Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is a reaction and a commentary to an article that looks at the state of AI from a very interesting perspective, from the perspective of Brooks' hypothesis in the Mythical Man month, that the nature of software development means that there is no silver bullet. So I find this a very interesting article, but before we go into it, let me just state a little bit about what's happening with AI right now from my perspective. So I think it's very hard to understand the real state of AI. And by AI, what I mean right now is large language models. There are many other parts of AI that are working fine. Like we have image recognition, we have sound or voice generation techniques. We have all kinds of technologies that have been around for a very, very long time. And they kind of came every decade or so, more or less. We had expert systems around the 70s. We had neural networks around the 90s. Which led to text recognition and image recognition and all this stuff. And then we had machine learning around 2010. So maybe it's every 20 years or so. And now we have large language models. And the pattern of these things is that they have gone up and down. So it's kind of, there was a big, these are referred to as AI summers and AI winters. So it's basically been an AI summer, people expecting a lot from the new development in artificial intelligence, and then it kind of went down. And I've been curious to see if large language models follow the same track. And right now, what we can see is that there's a lot of marketing involved, a lot of hype. There are a lot of people who stand to benefit from large language models, and they will hype it up. And think about if you look at the valuation of OpenAI, it has increased significantly in time. So we are literally talking billions of dollars right now. And then there's the question, is this a bet that they know they can win? Or is this a bet that they are making, hoping, because it's possible that the results will be very big? And honestly, I don't think anybody is certain that this will win, specifically in terms of a business. Because right now, if you look at businesses based on large language models, they aren't doing that great. But on the other hand, it's a new thing. It's a relatively new technology. It's hard to figure out if things will stay the same or get better or get worse. Okay, so in terms of using AI, I've been using it for a few things, and honestly, it's very impressive. So large language models they can do some things that are impressive, and they are interesting. But the biggest problem I have seen with them is that what they can do is create text, create images, create videos that are convincing, but not necessarily real, not necessarily something that might work or could work as a production level thing. And I've had this experience when trying to use ChatGPT to translate coding exercises in different languages, or generate some examples that I could start from and then modify. And it's been kind of a hit and miss. Usually it led to me working more than if I hadn't used ChatGPT or one of the LLMs. And but on the other hand, I've noticed how good they are as junior assistants, basically junior researchers, let's say. So if I were to do something today with an LLM, it would be ask random questions about things that I need and see what it answers, because it's very good at collating various sources from the internet and kind of giving you a summary of those sources. And sometimes these are wrong, but if you go, it cites the sources, so you can go and read through the source and you can see that they are wrong. Sometimes they are, oftentimes actually, they are very useful. So this is kind of where we are. I'm not certain, and I'm not sure anyone is certain where AI will go. There are 3 hypotheses that I think we'll discuss in commenting this article. And it's possible that it could be an AI winter. It's possible, again, it's possible that it will overcome the challenges and actually get much better. Although I'm not sure it's possible. We'll see. So it's really a bet right now, from my point of view. If you ignore all the hype, if you just look at first principles, yes, it's possible that it will get much better. But my feeling is that right now it would require something different, some different approach, some additional things. It will get incrementally better, but the question is, what are the costs of doing that? And if it will hit any benefits for a general audience, for businesses, like on a large scale. It's obvious that it has some benefits, but will it hit the benefits that are required to make all of this like a viable business in itself? And in case you don't know how these things are working in Silicon Valley, because maybe you're a programmer and you don't know how things work there, a lot of the work of these big startups is in getting investment, and people give them investment for the promise of eventually getting to a model that works. So even if a company is valuated today very highly, it just means that it's interesting. It has potential. It doesn't really mean that it's making money. That's basically how Silicon Valley works. In a nutshell. It's more complicated than that, but this is the short version. All right, so let's look now at this article. This article is called "Is AI a Silver Bullet?" It's written by Ian Cooper on his blog Staccato Signals. The link will be in the description as usual. And I've met Ian a couple of times. He's an interesting person, somebody I'd like to have a longer chat with. Let's see what he's thinking about. Written on June 24, 2024, Brooks' hypothesis, it starts with a TLDR. Brooks' hypothesis in the Mythical Man month is that the nature of software development means that no further order of magnitude improvements to productivity remain to be found, has proven remarkably solid despite 40 years of software history. Claims made that LLMs will cause significant changes to software development can be tested against Brooks' argument. Like previous attempts to find a silver bullet, such as 4GLs, if you don't know what 4GLs are, these were called, I think, 4th generation language. And the idea was to give a visual language, visual programming language, to non-technical people, so that the business people would be able to write the code, basically. And one such example that I think is still around there are remnants of this. It wasn't very successful in the end, but there are remnants of it, and you can see in a kind of flowchart libraries and flowchart tools where you can draw uh, a long-running process in things like Beanstalk, but there's also a language that escapes me right now, a visual language that you can use to define these flows, and then the system would run them. But the problem with this is that the level of detail, the level of precision required to write code is much higher than what non-technical people imagine, and therefore it ended up being used by programmers anyway. So this is why it didn't really succeed. But the idea of having visual flows for certain processes, I think it makes a lot of sense. So that's a good thing that remains. Okay, like previous attempts to find a silver bullet such as 4GLs, it does not seem likely that LLMs as a software authoring tool will succeed. In particular, like 4GLs, they suffer from the problem that because software spends most of its life in maintenance, the cost of change makes most improvement to the cost to author irrelevant. In fact, some rapid authoring techniques make maintenance harder and increase the lifetime cost of software. Now, this assumes, I agree with this statement, but this assumes that you cannot completely regenerate the software from your LLMs. And this is actually true right now, because if you give an LLM the same prompt, you will get repeatedly, you'll get different results, which means that you cannot actually rebuild this. But imagine if you had a system where you could write in a very specific way the kind of the requirements. I would say tests. That would be a good way to write them. And then generate the code based on those. That is proven to work. This would mean that every change would basically be event sourcing for software development. Instead of making changes on existing code, what you do is add a new test, rebuild, regenerate the whole thing, and then it would work. Problem is, this is a nice idea. It's very far from practice, from a practical application. So yeah, but if LLMs get much better, this might not be a hurdle anymore. They can and will add value as an expert assistant, but this cannot be an order of magnitude improvement due to the fact that it cannot impact the essential complexity, only the accidental complexity where no order of magnitude improvement remains to be obtained. As such, whilst AI tools may provide valuable additions to IDEs and other tools used for software development, they will not replace software developers or the need for high-level languages. So think about it this way. Somebody put it in a podcast, I don't remember who, but it was a really good point. Every time software development has automated more and more of our jobs, but the demand for programmers has increased constantly despite that. So that's interesting. If the same pattern stands, it's likely that the demand for programmers will keep increasing even though we are using AI to develop software. And so, yeah, there's a big if here. We don't know. Maybe it will, maybe it won't. One thing that I think is true is that it will change the way in which we write software, but the question is how much? What will be the changes? And I have a feeling for some of them, like more research can be done using these assistants. Maybe you can get links to better solutions. maybe they inform your decisions, your design and architectural decisions. So that's a good thing. But on the other hand, generating the code, it doesn't seem to work that well, honestly. So at least code that is production ready working. No, we still need to modify it. And my feeling is that often you work more on generating the code than making it work than on writing it yourself from the beginning. Right, introduction. When it comes to LLMs as a developer tool or replacement software developers, popular opinion seems to predict one of three main outcomes to the current boom. AI developers. Under this model, software developers no longer need to write code. Instead, the task is now done by an AI coder. Subject matter experts interact with an AI that does all the work of writing the code. AI assistant. Under this model, software developers get assistance for common and repetitive tasks from an AI assistant. This increases their productivity by how much becomes the concern. Does this reduce developer headcount? AI winter. Under this scenario, the LLM revolution fails to deliver the advertised gains and may even lower productivity because in the longer run, it gets in the way as companies who outsource their code to an AI are forced to do so much remedial work. It would have been less expensive to hire a software engineer, write high-quality code. For anyone considering a career in software development, the difference between the outcomes is stark. In one, the job of software engineer would seem to disappear for most people, automated into obsolescence like the weavers. In the second, the job may change, but the number of people the industry employs declines, making it particularly difficult to obtain entry-level roles. In the third, wider AI research is set back by the LLM hype cycles collapse. Yeah, and one thing that's particularly interesting here is that AI assistants make sense, particularly when they generate the code, they give you solutions and so on. They make sense when you already have the experience to write the code yourself. And this is why he's hinting at this problem that entry-level roles might be more affected than people who are already in this position of senior programmers and just need a little bit of help. Or the assistance of AI will help them move faster because they stop doing many of the or a lot of the menial work. And so that's a longer term problem, because if you fail to add more people in the industry, it eventually gets old and and it doesn't work anymore. So there might be a little bit of a problem, and it's very hard to see how this will adjust. The agenda here is the productivity of software development. The hope is that AI will make software development cheaper. For AI maximalists, software engineers will no longer be needed. Even for the minimalists, less of us will be needed for a given task. The optimists spin this as more software engineers available for work, the pessimists as more engineers out of work. Predicting a future is fraught. A lot of people don't like to make predictions but adopt a wait-and-see attitude. This is particularly true when we begin to talk about fast-moving field like AI, and also with a lot of hype surrounding it. It's very hard to right now to make the difference between what is noise and what is real. You can, up to a certain point, do this by trying the different AI tools, but the problem is that this doesn't tell you where the field will go, right? We actually don't know. And it is worth pointing out that I'm neither involved in frontier AI research nor do I have any formal background in AI, so I contribute to the debate. The productivity of software engineers is not a new problem. For years, businesses have been looking for the silver bullet that will deliver radical changes in software productivity. The software crisis was the term coined at the NATO Software Engineering Conference in 1968 to describe the difficulties in writing software, cost overruns, loss of money, and fatal accidents. Whilst we have made many strides in how we do software engineering since that time, history suggests that progress is incremental and not revolutionary. This is an interesting point, I think. It's another thing that is very hard to say about AI is, will this be revolutionary, or will this be, is this the revolution that happened until now, that we now can generate text that is meaningful and images and videos and that are relatively convincing, at least some of the time? And was this the revolution and now we start doing incremental work? Or is the revolution coming? Of course, OpenAI and other companies would like you to think that AGI is coming, the artificial general intelligence. I'm skeptical about that. We haven't yet seen any sign of that. Okay? But we have seen we have seen a revolution initially when ChatGPT first came out. And that was impressive, really. But then all that has happened since then has been incremental, because it's basically the same thing but applied to different languages. Text is a language, music is a language, sound is a language, video is a language, code is a language. It's kind of the same thing applied and with the same problems. So it seems like right now we are in the incremental phase of AI development. Will there be another revolution fueled by the billions that are flowing in investment? Well, I don't know. Nobody can tell. If we were to judge by previous patterns in AI, the answer would be most likely no. But really, we have no idea. Software developers are subject to the law of supply and demand. As the information age has created an insatiable demand for software engineers, so the cost of software engineers has risen. If the costs rise enough, it becomes economically attractive to invest in increasing supply or productivity. This is a part of the software crisis. Retraining people as software engineers, one non-computer science graduates into software engineering, more recently boot camps. Looking for silver bullets, improvements to productivity through increased language abstraction, OP, functional programming frameworks, etc. Creating low-code tools to make subject matter experts software engineers. Remember when low-code tools were the big hype before LLMs? I still do. Whatever happened to those? I wonder. Outsourcing to increase the supply via cheaper foreign labor. AI is just another attempt to fix the problem. Yeah, in terms of the software industry, I think that's correct. In a more general sense, they are trying to do much more than that, but yes. Not talking about LLMs as a component. This post is not about the usage of an LLM as a component in your system to solve a particular problem, such as a customer chatbot. It just focuses on how LLMs are likely to impact software development employment. Yeah, so, and honestly, I'm starting to get annoyed by all the tools that tell me we now have AI. I'm not very interested in that. I'm not interested in chatting with your system. I'm not interested in you generating stuff for me. Usually what I do implies writing a certain level of content, creating a certain level of learning exercises, a high level of learning exercises, learning materials and so on. And most of the things that I see, because I occasionally try the LLMs to see what they generate, and they are either wrong, they miss the point, they can't explain it properly. So, no, I'm not interested in that. I am interested, though, in getting some compilation of things about a specific topic occasionally. A valid criticism is that this post does not consider the possibility of LLMs solving the essential complexity of some problems and the impact of that on software developer employment. The likelihood is that this impacts specific vendors where LLMs are a good fit for specific challenges over others. The discussion is outside the scope of this post. So I think there are two discussions here. One of them is, are there specific parts of software development that can be impacted by this? For example, if you are building translation software that might be impacted by this, or it can benefit from adding LLMs. If you look, one thing I'm thinking about is generating Docker files and generating all kinds of this menial work. And maybe before it was a person doing that, but now you can do this with a prompt and some checks, some quality checks afterwards. And maybe there are some specific problems that are solved faster by LLMs. But this will be just pockets. And the other discussion is, will this affect software development in general? Like, will, for example, 10% of programmers stop having work because they are replaced by AI tools? No, this is a completely different problem. And I like that he's focusing on the general one rather than particular pockets. Pockets will exist always. For every automation we did in software development, there were pockets that were affected, and there were other parts of software development that were not affected. What is software engineering? The primary activity for software engineers is the creation of computable models. Presented with a set of functional requirements, we figure out how to turn that into something a computer can do. This involves two steps: modeling the problem in a computable fashion and turning the outcome of that, the design, into code. Instructions the computer can understand. Both of these steps are significant, although it doesn't really matter for this discussion how we define the modeling process. Use cases and UML diagrams, CRC cards, boxes and lines on a whiteboard, or a TDD test list, or other code-based exploration of the model. A key problem here is that productivity improvements typically address only the second step, turning a design into code, and ignore the first step, creating the model. Yeah. Well, so as I said, I believe that the fundamental problem of software development is taking very vague requirements and refining them into very precise code. The level of precision required from code is much higher than people who never wrote code imagine. Sure, you can use today tools like LLMs to generate HTML pages and all kind of stuff, but they mostly don't work that well. They don't cover all the requirements that a modern HTML page has, and so on. So there are a lot of limitations to that. So in the hands of somebody who knows what they are doing, those tools would help maybe implement this quicker, maybe. But there's a big challenge. This is one-time thing. You generate one HTML page. If you try to generate a whole site, things start to get a little messy. It's not that easy. So, yeah, what he calls modeling, what I think about the whole process is basically this refinement into precision, where code can be a part of it from the very beginning, like it is in test-driven development, or can be left closer to the end, like it is for other types of designing first and then implementing. Ironically, this misconception may have been exacerbated by agile software development techniques that tend to prefer exploratory modeling with code, fooling people into believing that modeling was not happening, just turning designs into code. This is not true. Agile engineering practices just seek to use code for both modeling and instructions for the computer, and are themselves a reaction to case tools. See below. This is true. I've often made the case that test-driven development is actually an exploration technique. You explore the problem domain using tests, and I think the way most people do test-driven development is they search the implementation. But in reality, what you should do is to try out different approaches and kind of explore the solution space. And the tests help you do that. This is a necessary step in design that too often we skip, or we shorten too much in software. But if you look at every other design discipline done properly, you have this step of exploration. Like no designer worth their money and their experience and their profession will come with a single solution to a problem. They will come with 3, 4, 5 alternatives, and then pick one of them, often in collaboration with other people, and then move on with that. But in software, it tends to be, well, it's easier to do this mentally, and we kind of kid ourselves that we try things out, but we haven't actually tried them to the level where we should. So one thing that TDD can help you with is this exploration phase. But you have to let go of the implementation, of the implementation that you envision. And that tends to be hard for developers who are taught that every problem has a solution and you need to write the solution. No silver bullet. In a 1986 paper, Fred Brooks wrote a paper, No Silver Bullet, that suggested that further improvements on developer productivity would be a hard one. Indeed, Brooks offered that there would be no order of magnitude increase within the decade. Brooks identified that this was because there were two facets to the task of software engineering, and only one could benefit from productivity improvements. Essential complexity, the work involved in modeling a solution to a problem. Accidental complexity, what is required to turn that model into computer code, in essence, writing code. Yeah, I think it's slightly more than that, but okay, we'll go with it. Brooks' argument is that productivity gains can only come from reducing accidental complexity. The essential complexity of a problem is irreducible. I believe the hard part of building software to be the specification, design, and testing of this conceptual construct, not the labor of representing it and testing the fidelity of the representation. All of the technological attacks on the accidents of the software process are fundamentally limited by the productivity equation, time of task, sum of I frequency I times time I. If, as I believe, the conceptual components of the task are now taking most of the time, then no amount of activity on the task components that are merely the expression of the concepts can give large productivity gains. Frederick Brooks, The Mythical Man Month, Essays of Software Engineering, as Anniversary Edition, 2nd edition. Brooks proposed that unless we assume that we have yet to solve 9/10 of a problem from the accidental complexity of software engineering, no innovation in software engineering can produce an order of magnitude productivity jump. For Brooks, we have already crossed the point where we have made the really big gains in productivity. Improvements may chip away at the accidental complexity, but not enough complexity remains to radically shape up how we write code. The reality is that 40 years since Brooks wrote his paper, most of the tools of programming have changed little. They have been incremental improvements, OP frameworks and libraries, package managers, agile engineering practices, but no order of magnitude increase. This could be considered proof of Brooks' hypothesis. Any high by the LLM maximalist surely has to overcome Brooks' arguments. Yeah, so the only thing that might happen is that LLMs will figure out how to solve parts of the essential complexity. For example, by looking at how problems were solved and then giving you solutions that fit a new problem. Theoretically, this is possible. Practically, we'll see. And given how inaccurate the code generated by LLMs is today. Generations of languages. Most of our efforts to improve productivity are focused turning the design into code. We first program computers by flipping switches. Over successive generation of languages, we have moved the level of abstraction up from being physical inputs into the machine to something that can be typed and understood by a human. We call each successive raising up of the level of abstraction from the machine a language generation. The generations can be understood as follows. Each higher generation would be implemented by generating code of the lower generation. This is useful as it allows the existing tools from that generation to continue to work. We can thus progress incrementally. So a 3GL compiles to a 2GL, which is assembled into 1GL, which directly instructs the machine. More formally, first generation machine code, binary input of codes understood by the chip, originally by operating switches on the machine. Second generation assembler, human-readable macros that can be assembled into machine code. Third generation, high-level contain control structures, variables. Originally, a compiler turned these into assembly, which was then turned into machine code. A modern compiler turns statements into object code. An interpreter turns statements into bytecode, which it then executes. High-level languages include C, C++, C#, Go, Java, Pascal, Rust, Zig, and many other languages used today. Fourth generation declarative, not imperative statements. Naively, the 4GL generates a 3GL output that is then compiled, but just as 3GLs don't strictly work this way anymore, not all 4GLs generate 3GL statements, but instead directly create object or bytecode. 4GLs include visual design tools, Visual Basic, Access, Power Builders, equal Windows, domain-specific languages, HTML, WPF, HCL. I don't know what the HCL is. Data, DSLs, SQL. Fifth generation is questionable if a 5GL has ever really existed in the sense of generation. The term was co-opted for AI programming languages in the 90s. I told you, 90s were a good time for AI, such as Prolog, but they are not really raising the abstraction to be a true generation. We'll ignore them for the purpose of this discussion as they have had little impact outside academia. The triumph of 3GLs. Today, most of us use 3GL. We talk about compiling or interpreting our code, and we rarely need to deal directly with assembly or bytecode. This has proved to be a productive level of abstraction. I entered the industry at the point where inline assembler was still enough of a performance hack that you had to know a little bit of assembler, even if you're using C or C++. What do you mean when? I think this is still done today for specific applications. I think, well, shaders for games or heavily visual applications, I think, are still written in a kind of assembly. So yeah. Alongside that, with 4GLs in specific scenarios where they have proven useful, some of the most common examples that spring to mind are SQL to work with data, HTML, CSS to work with web documents, HCL, Terraform, okay, to declare infrastructure. I know about Terraform, I didn't know the language is called HCL. In addition, many developers use visual designers to generate code for desktop and mobile UIs. Oh boy. This explains some of the problems I see. Although 4GLs have thrived in these niches, the general purpose programming language, the 3GL has remained the workhorse of our computing abstractions. 3GLs have increasingly extended their syntax to support a mix of imperative and declarative statements, for example, enqueue in C#, and generic code from these 4GL statements. Why did 4GLs only excel in niches? Perhaps the domination of 3GLs is surprising. If a 4GL can raise the level of abstraction, it will make us more productive. Why have 4GLs remained in niches? Why have we not shifted up a whole abstraction layer? Well, because it's more complicated than it looks like. And raising the abstraction does not always lead to faster development. Sometimes, higher abstractions have limitations. And I think many of these things, when you go to 4GL, the abstractions kind of hit their limit. There have been many historical attempts to do just that. In the mid-90s, it seemed that 4GLs might dominate software development. It would not have been unusual to find most of the code in an enterprise being written in Visual Basic or Power Builder. What happened? The problem is a classic trade-off. When many innovations in the space took for the accidental complexity of authoring software, they added into the accidental complexity of owning that software. This is a problem we repeatedly forget and relearn. Any successful software will be changed as the need of its users change. Put that on a poster in your office. If your program is successful, if your product is successful, it will change. You need to be able to change it. Most of the lifetime of any successful piece of software will be in the ownership phase. During ownership, our costs will be the cost of change. So to reduce overall costs, we need to reduce the cost to change our software. The first term of what I've dubbed Constantine's equivalence then is that the cost of software is approximately equal to the cost of changing it. This is a quote from Kent Beck's book Tidy First. Whilst improvement in the productivity of authorship initially prove attractive and gain traction, because the cycle has not reached the point of maintenance, the problem of ownership inevitably shows up as we have to live with the costs of what we authored. Optimizing for authorship is usually a poor trade-off in the long run, as we spend more time on maintenance and modification than on creation. In some scenarios, software is highly disposable, and in those contexts, low authorship costs may be an advantage, but for most software, if it becomes successful, it will spend much longer being owned than author. So this is where the cost lies. Yeah, so for example, one place where I think LLMs might have a future for this disposable software is one-time data migrations. Like you have data in a system, you want to move it to another system, and you need to kind of mix and match things. I think having lived through that experience, an LLM might have helped there. The problem for many tools in the 4GL era is that whilst they made software easier to author, they made it harder to maintain. Yeah, that's true. I've seen Visual Basic code. And it was really fast to create a new application. And honestly, a lot of the selling point back then for Microsoft was, look, you can create new applications very easily. Click and design, use the designers to make things work and so on. But then the industry kind of caught up to the fact that maintenance, it was so easy. And you need to kind of structure your code in ways that help you change it. Otherwise, it's not really helpful. Case tools. In the 1990s, there are large players looking at 4GLs backed computer-aided software engineering or case tools. Case promised to use visual designs, tools, and generate software. Case tools include what we now call low-code environments and model-driven engineering. These are just current iterations of these tools. Case tools include both workbenches and environments. Workbenches. The goal of workbenches was to enable experts to design software without software engineering. Good luck with that. So, you see, it helps for creating applications. You can do the first pass. And there's something to be said about building a prototype that does roughly what you want as a non-technical person and then passing it to a technical team. I think that's a big value, because we can often understand better by poking around an existing system, and then figure out the edge cases. I think that's a valid thing to do. But believing that you can do software design without the proper experience, it's a bit too much. Tools like DataEase, Microsoft Access, or HyperCard offer simple line of business application development where all that was needed was a form editor and a database. The popularity of many of these tools led to the growth of shadow IT, where business departments developed their own software outside of the traditional IT department. I remember Oracle Forms. Oh boy. Given the backlogs faced by IT departments, they seemed the solution by decentralizing the provision of IT systems. The problem became that the department simply created new software developers, albeit unskilled, with workbenches. Any tool requires training and experience to use. It doesn't come as part of the skill set of being a subject matter expert. Workbenches shifted many subject matter experts into software developer roles. At first, this was empowering because decentralized IT empowered end users to solve their own problems, often avoiding long backlogs and costs. But such departments then hit all the problems of ownership. When individuals left, departments have no backfill or found it difficult to transfer software not written with the idea that others might maintain it. In many cases, they were forced to turn to IT for further maintenance. Okay, so many people talk about 4GLs, and that's true. Everything he's saying is true. But let's not forget the most spread out programming language used for running businesses today, and that is Microsoft Excel. Yeah, there are many programmers who build Excel applications, let's call them, and then you have the ownership problem. How do you fix this? IT had engineers skilled in 3GLs. These engineers then rewrote these 4GL workbench applications in 3GLs. Overall, the cost was higher than having IT writing it in the first place. In addition, compliance and risk concerns emerged as the management of data spread throughout the organization, which required the application of software engineering discipline, but was now uncontrolled. Of course. Some organizations even banned end users from writing their own software due to the costs of this shadow IT hangover. Arguably, a spreadsheet is also 4GL workbench. Good catch. Although it is not usually bucketed alongside other low-code tools. Yeah, so we have an interview on this channel with Felina Hermans, and she actually proved in her thesis that Excel is a programming language. Yeah. So, and it's actually very, very used for business. In addition, these tools worked well for a range of built-in scenarios, but outside of those scenarios could not work at all. They could not be extended. When these changes were needed, the business had to reach out to IT. Again, to meet these new needs, IT often had to rewrite the software created by these workbenches. As a remedy, workbenches began to transform by adding programming in a high-level language, effectively becoming developer tools. The developer versions of these workbenches included tools like Visual Fox Pro, Visual Basic, and Power Builder. These developer versions could be extended more readily by 3GL. Yeah, you would write some code. They were a compromise, trying to take the benefit of forms-based programming and reducing the cost of writing UIs, and married to the ability to extend with 3GLs. And this has led to Windows Forms and later to Windows WPF. What was the Windows Presentation Foundation? They will often be used to replace tools written by a shadow IT workbench. These were successful in the 90s, but developers found that their limitations, particularly their orientation around form-based programming, were difficult to escape, particularly to capitalize on changes in technology. Because these tools could only be used to write form-based software, they were not suitable for other applications. Their skill sets were seen as less flexible than those of true TGLs and thus less valuable, often resulting in developers looking down on those using these tools. In turn, that made these jobs less desirable. These issues came to a head with the rise of the web. These workbenches focused on rich client development. With the move to the web and the implicitly distributed nature, these tools were left behind. Developers working in these skill sets needed a path out and onto the web if they were to remain relevant. While tools tried to catch up, the pace of change of the web outpaced the redevelopment of these tools. Yeah, but there are still some of these, like, what's the name? There are some CRMs, which I don't remember right now. They escape me. They have their own language. There's a whole thing about configuring them. They are very complex, deployed to a lot of different people. Things like Salesforce, but not only. So, and honestly, Salesforce has also moved towards a more web service, web APIs kind of approach. So, yeah, it's once again, there were some remnants of this, and they still are. Quickly, frameworks replaced workbenches. Most of the benefits to developers in using a workbench tool could be provided by a framework. For example, Microsoft created web forms for .NET. Man, it's like we talked before. As a way to leverage the form-based programming model and help the workbench developers transition onto the web. That was a good transitioning technology, but it was not great. It was not something that we would use today necessarily. The problem was that while workbenches offer productivity, they could not adapt well to change, either to changes or to how the business wanted to work or to changes in technology. Of course, the complexities of the form-based stateful abstraction of web forms over the stateless protocol of HTTP soon began to tell in maintenance. Yeah. So one of the problems is that they were trying to keep state, and they would keep sending the state back and forth. It was before JavaScript was allowed for so much interactivity. So you had to do, if you wanted a little bit more interactivity, you had to do it on the server. Web forms were rapidly eclipsed by domain-specific language-oriented frameworks like Ruby on Rails. Yeah. Nonetheless, workbenches continue to exist today for use by end users and developers. For example, Microsoft Power Platform. I have no idea what this is. For the purposes of this blog, it is worth noting that few developers today fear that they will lose their jobs because end users can use a workbench like Power Platform. Environments. UML extended simple O diagramming notations to allow them to become a 4GL. As an aside, a lot of people feel that extending UML in this way is what killed UML, and its predecessor notations with it as a useful O diagram notation. Yeah, the problem with UML right now is that it defines about 70 different types of diagrams, and that is just overwhelming. When we could really benefit from using UML, but we really need to use the subset, like use cases, a state diagram, one of the interaction diagrams. Class diagrams are not that useful, but deployment, for example, yeah. So there are some useful things there, but it's like in the order of 5 to 6 types of diagrams. And in the meantime, we got, especially if you are on the cloud, you're probably more used with the AWS notations or the Microsoft, because they offer you the icons to use in your modeling. They were good like that. instead of using the general language. You have a more specific modeling language. In this view of software engineering, analysis becomes new key role, capturing use cases, developing analysis and design models in UML, and generating much of the software, or at least scaffolding much of it to fill in some blanks. The reasoning does make some sense. If code is just the accidental complexity of modeling the essential complexity, why not focus our tooling on modeling? And then just generate the code. The implications, for example, no longer caring about the high-level languages you generate the code in seem to have value. But the case revolution never happened. Why? Well, I believe it's because it doesn't quite work like that. You have a feedback between code and design. Because as much as people want to separate modeling from code, the code is the design in the end. Always, yeah, that's my belief. The structure of the code matters. It's not enough to just model it. The problem turns out to be that this creates two models, the one in the analysis tool and the one in the code, and they can become out of sync. UML could not capture all of the design. A graphical notation had many ambiguities and details that needed filling in via programmer using a 3GL. This breaks the whole edifice of the environment. As soon as the programmer began to modify the generic model, the two became out of alignment. Further change became complex because the tool had to account for change made by the programmer. It required round tripping, model, code, and code model. But round tripping never worked because UML was not complete. Once again, the same problem surfaced for 4GLs used in this role. The cost of software is in ownership and thus change and not in authorship. Because these tools make software harder to change, they were more expensive in the long run. If we are optimizing for readability, more code faster is not better. Put this on your work. As an aside, two movements can partially be seen as a reaction to the failure of environments, both of which focus on code as the primary artifact. Agile, which favors working code over modeling tools, domain-driven design advocates may note its admonition to use one model expressed in code as a reaction to environment-led approaches. This emerged precisely because it proves to be easier to model in code than in a graphical notation. Yeah. Code generation. Software developers have used code generation as a technique for many years. Typically, the goals of both productivity by removing boilerplates or repetitive work and heavy lifting for junior developers by creating a paint-by-numbers framework for them. So we did a whole video on code generation, and we looked at various types of code generation. And the general conclusion is that can help with some things, but often it doesn't. Because there is, again, the round tripping issue that he's mentioning. So I'm going to skip a little bit from this because it's the same thing. It basically, code generation increases maintenance cost. In many cases, code generation is replaced by frameworks. The advantage of framework is that you can fix the issue once, create new features, and simply redeploy, thus reducing the cost of ownership. Finally, code generation often suffers from the problem that it does not build understanding. Because the team did not build a code app or use publicly available well-documented frameworks, the onboarding costs are high. Yeah. DSL revolution. We mentioned earlier that Ruby on Rails created a shift towards the framework as the primary way to reduce the accidental complexity of writing websites over the workbenches. In the 90s, part of the success of Rails was due to Ruby syntax making it possible to use many declarative constructs within the language, Rails creating a DSL for web programming. And DSLs were supposed to be a revolution, and I still believe they are extremely useful. But the problem with DSLs is you need to design a language, and not many people are language designers. And you need a very specific set of skills to be able to build a good DSL that actually helps your team move faster. I still believe it's a valid approach, although I guess we'll see that the article does not agree with me. But I believe it's a valid approach, but it's still tough to do. It's harder to do than just writing the code. So the DSL revolution never happened. What happened? As we'll now be familiar from other failures, DSL suffer key issues. Problem of modifiability. When the domain changes, you first need to change the DSL before you can express the new concepts. Yeah. And DSL developers have specific expertise, language parsing and building tools via language workbench, and work often queues for those developers, slowing throughput in maintenance. Problem of onboarding. Everybody needs to learn your DSL. Yeah. Problems of feature set. You can do 80% easily, but 20% not at all. Yeah, and that's valid for almost any programming language. But the general programming language, or what he's calling 3GLs, they are better at this. There are very few things you can not do in any one of the modern, highly used programming languages. Problem of tooling. Yeah. So this is the thing. When you're doing a DSL, you're really building a language, which means you need to have language designer, you need to have some kind of compilation. There are inner DSLs and outer DSLs. So there are inner DSLs that you can create with particularly in dynamic languages like Groovy. You can write DSLs inside the language. There are some mechanics that allow you to do that, and that's easier. But if you want to do, I think it's called outer DSL, what you need to do is to define your lexer in a specific, your lexical and your syntax and all that in specific tools like lexers, and then create the language from that. And you basically have a compiler built into your language, more or less, or your build process. And it will be limited because designing languages is complex and so on. Ultimately, DSLs work best when the domain is stable and we build a tool chain to support them. UIs, HTML and CSS, data access, SQL. Yeah, that's true. But even in areas like infrastructure as code, hard to debug feature set makes it arguably easier to use something like Pulumi than Terraform. See also AWS CDK Aspire. The dream of domain experts writing code over software engineers reinterpreting the requirements often fails because it tends to create write-only software, even assuming domain experts are willing to become DSL programmers in the first place. In addition, the goal of the business user writing software via a DSL was always a myth. Yeah. Once again, the biggest problem is precision. Maybe you can figure out the one part of the rule. Let's say you want to write business rules. You might figure out a part of the business rule, but when you start asking all those pesky what if questions, you realize that there's a lot more than that. Yeah. 4GLs also declined because we moved into the era of software as a service. Instead of most businesses building bespoke software, the target of much of the 4GL revolution, many businesses switched to using SaaS offerings via the web. This is because most businesses don't want to turn their subject matter experts into shadow IT. They want to provide them with tools to do their job, and SaaS provides a way to do that. The demand for shadow IT reduces under this model, that it is meant mostly by SaaS tools. For the SaaS vendor, the goal of empowering end users to write code over software developers fades away. There are few advantages and many disadvantages of shifting code into the problem space than remaining in the compute space. The arrival of prompt engineering. What can the past tell us about the likely trajectory of LLMs driven by prompt engineering and their impact of software development? To recap our key points so far, essential complexity cannot be reduced. Improvement to tooling just reduce accidental complexity. Reductions to accidental complexity must focus on ownership of software, and not the authorship of software spends most of its life in maintenance being changed. Interestingly enough, Brooks considered the impact of AI on programming back in 1986 and divided applications into two buckets: automatic programming, AI developers, and expert systems, AI copilots. Both are attempts to find a silver bullet to the software crisis through AI. For now, I'm not going to consider the idea of autonomous agents writing software and attempt to increase the supply of engineers through the use of AI workers. Nothing about LLMs indicates to me that they can act autonomously. Yeah. They require humans to give them tasks, in other words, to program them. Yes. Well, so here's one thing you might do, although I don't think it's practical right now. One thing you might do is to take the specifications, use an LLM to extract BDD statements out of those. Review that, but you still need people to do that. Turn that into smaller level tests. Basically split every BDD statement into a smaller level test. Review that, give it to LLMs, and they should go through the cycle of write code, red, green, refactor, basically. Write the test, write the code, refactor, write the code, and so on. Get a result. All the tests are passing. The tests are reviewed. If some tests are not passing, you can go and look why. And then you have this. And then if you need any changes, basically redoing everything from the scratch. But this sounds overly idealistic right now. I mean, in theory, you could have agents for each of these tasks. You could have an agent that is trained into extracting the BDD statements. You could have an agent that is extracting the lower level tests. You could have an agent that is writing the test, another one that is writing the code, another one that is refactoring, and so on. So in theory, you could do all these things, or maybe some other approach, but I think the TDD one is the most mechanical one that we have right now, the one that we can approach the easiest. But is this practical? Is this possible right now? I'm not sure. I don't think so. I think the level of mistakes that this system will make is very high. But maybe there's something to be said about the adversarial models. You know, one that keeps pushing tests to you and the other one that keeps writing the code to match those tests. Maybe there's something there. I don't know. It's not necessarily or strictly related to LLMs. It's a combination of different AI techniques. Automatic programming. AI developer Sarah Case Brooks calls automatic programming. Automatic programming is an attempt to give a computer natural language instruction to author code. Can an LLM instead be used to allow natural language to specify requirements in a given domain that can be used to generate code? If so, does this lower accidental complexity? Many proposals for AI replacing developers pitch themselves as a better language workbench. More of the app can be declaratively described in natural language and the code generated. Attempts at natural language programming have often only allowed the constrained use of language, of course. Obviously. Once again, the problem of precision. If you want to obtain very precise things, you need to have a more constrained language. Or a way to turn less precise things into more precise things, which to the best of our knowledge right now, only people can do. And through a lot of collaboration. The promise of an LLM for automatic programming is that you can use prompt engineering techniques to write the code. In this slide, the LLM is being used as a 4GL as we are using it to generate 3GL statements. We do have the ability to generate 4GL statements too. I'm not sure that really makes an LLM a 5GL. Our 4GL will consist of prompt engineering statements, but rather than being truly declarative, describing what we want, prompt engineering uses triggering, pushing the LLM to trigger a response based on solutions to the problem it has been trained on. The question is whether we can devise a toolchain or set of techniques for use with software written via prompt engineering statements that can solve the problems that we had with 4GLs to date. Modifiability tools, feature set, onboarding. Modifiability with prompt engineering to trigger the LLM into generic statements in an existing 3GL. By definition, it can do anything else. This means that either evaluation of that code can only be done by someone skilled in a 3GL, or the tooling needs to reach the point where we can maintain software written via prompt engineering without dropping down to the 3GL. And guess which one of these is most likely? I think the first one. Whilst an LLM can only generate statements in a 3GL or 4GL, as of now, they require human action or review. While this remains true, we'll eliminate one of the largest benefits that automatic programming seeks to obtain. Today, LLM-based AI developers offer different ways to author the code, but still require software development skills to verify and use the results. We have seen before that the need for oversight by someone skilled in the 3GL tends to resolve work shifting to the 3GL to avoid multiple models. If the technology reaches the point that it can do self-verification, such as self-debugging, then we move closer to enabling the subject matter expert can use the tool directly. At this point, translation issues between the individual who understands the essential complexity of the problem and the code are removed. In theory, accidental complexity fades away. The risk is, though, that prompt engineering is just a replacement for one form of accidental complexity which we are good at solving, with another form of accidental complexity, how to elicit the computational model we want via prompt engineering, which we are less good at solving for now. The current state of prompt engineering, which is spells that must be incanted to work, just looks like another form of accidental complexity. Yeah, so this is the big problem. Writing code, and once again, it's a problem of it's the same problem of getting the tools to do precisely what you want. It's a problem of precision. If you want the LLMs to generate precisely what you ask them to, you need to be very precise in the way you write the prompts. And then the question is, why not writing the code? Because if it's at the same level of precision, what advantage does it bring? Okay. I'm gonna skip a little bit over this. There's a little bit about human eval. Okay. So as soon as we have any problems or change requests, the developer is faced once again with a classic round-tripping problem. They have to choose between amend the code and abandon for the change via the prompt engineering statements, alter the prompt engineering code to generate the change code. This is the trade-off we have seen before. Eliminating the accidental complexity of authoring code has less value than we think because code spends most of its time in maintenance. So the maintainability of the code is more important than the speed to author it. Yeah, so I think that the basic problem here is the prompt will still be code. It's a different type of code. It's maybe a higher level type of code. It still needs to be precise. It still needs to be written in a specific way, in a specific language. Only as he's saying, we don't really know what language right now. We're kind of figuring it out. We don't yet know how to make LLMs kind of do the things that we want. We can have a conversations with them, sometimes not great, but not always get a good answer. Tools. Due to the reliance on code generation, the toolchain for LLM-based automatic programming ends up being the same toolchain that developers use to test, debug, and observe code today. If LLM-generated code has a bug, how do you generate code without that bug? It is possible that feeding output back into an LLM allows it to correct itself, but the process is often slower for the engineering than simply applying the fix directly. Given we use the existing tooling, though there is certainly no silver bullet for accidental complexity to be removed by using an LLM tool, we must ultimately switch into using 3GL-based tooling. Feature set. Of course, an LLM driven by a prompt can only ever hope to remove accidental complexity by providing solutions based on prior art in this space. This is the feature set problem. Many problems of accidental complexity are today solved by framework or libraries. For the LLM to novel domain problems, it is necessary to train LLMs on existing domain-specific solutions, but this run afoul on the need of exponential increase in data, which we may not have. Yeah, so the amount of data required to train an LLM is staggering. Basically, right now, one of the challenges that OpenAI is facing is that they have exhausted the internet, which sounds ludicrous, but that's part of the problems they are facing. So this means, an LLM is good at doing the things that it's trained on, and if you're trying to solve a completely novel problem, guess what? The LLM will not give you the right answers. Okay, there is a little bit of onboarding. Limited to accidental complexity. The LLM cannot solve the problems of accidental complexity when must be tackled via the accidental complexity of our prompt engineering. Given Brooks' assertion around accidental complexity, this can give an order of magnitude increase in productivity. Even if we manage to create a toolchain that resolves many of the problems in DSL's prompt engineering, solves accidental complexity but not essential complexity. Developers just use different tools to do the work, but they are still developers. Yeah. And expert systems. Copilot tools are classic expert systems. With LLMs, they provide probabilistic advice on what code to write. Provided the LLM has been trained on similar code, you should be able to help, as Brooks predicted, separate application complexity from the program itself. This is already a proven use case. The capacity of an LLM to act as an expert system via Copilot seems to offer valuable assistance in reducing accidental complexity. As ever, some developers benefit more from expert assistance than others, and the tendency of LLMs to hallucinate libraries that do not exist means some developers will turn it off as less efficient. Yeah, we talked about this before. Some of this code generation, it doesn't really work. Silicon snake oil, what conclusions can we draw from this? The discourse around LLM capabilities is dominated by inflated claims and snake oil salesmen that drown out reasonable assessments of claims for this technology. Sometimes it can feel hard to assess. Is it just silicon snake oil? Is there something more real here? The NVIDIA CEO may be successful at driving up his company's share price, and after all, that is his job, but I would be very skeptical about his claims at this point. Yeah, he stands to gain a lot, and the company he runs from this. And honestly, it's his job. So, saying AI will develop exponentially because we'll sell a lot of GPUs then. But of course, he does that. AI developers. This seems unlikely to bear fruit in the next 10 years. The burden of proof for faster advances than this has to lie with its advocates who need to prove they can solve the problems of onboarding, modifiability, feature set, and tooling. Yeah. AI assistant. This has already borne fruit. Perhaps not the full spectrum of expert system for developers that Brooks envisaged 40 years ago, but certainly progress towards it. This will reduce the accidental complexity of development, although not by an order of magnitude, or not tackle the essential complexity for which human developers are still required. I agree. Will AI assistance result in layoffs or lower hiring? Increased productivity does not always imply layoffs. Subsequent shifts, for example, 2GL to 3GL, led to increased employment. Yeah. Most developers don't lose sleep that Power Platform or Excel will lose them out of a job, although in many cases a spreadsheet is exactly the tool that the end user needs, not your code. Yeah. The reality is that we have made successive attempts to move developers to the higher ground of domain problems, the essential complexity, and away from the low ground of technical problems, the accidental complexity. Domain-driven design was centered on the idea that modeling the domain is the key problem, not the accidental complexity of writing software. There's different developments as well. It is interesting to know how those old ideas, TDD and DDD, that many have evangelized, thrive in this world. TDD becomes a powerful tool when you ask the AI to implement code for your tests. I'd like to see that. Domain-driven design becomes a powerful tool when you focus your modeling efforts on the domain. Using TDD to model behaviors, using AI help to implement those behaviors, stitching those behaviors together is a powerful technique today. It only becomes more powerful when working with an AI to help you. What do you need to do today? Learn how to use an AI assistant, but become familiar with Copilot tools, but also develop prompt engineering skills so you know how to get results. This will be like learning any new skill. At first it will be slow, painful, and counterproductive, so you may not want to do it under pressure. That is the position of all of us right now. But as you play with these tools, they will become part of your toolkit, and you can evaluate their usage of just write the code based on what is more performant for you. Understand AI engineering in the context of how to use AI as a middleware. This may be as, if not more important to your professional development than worrying about 4GL appearing. Okay, basically what he's saying is that he's skeptical. AI winter. The AI field has certainly grown beyond the disappointment that led to the Light Hill Depot and first AI winter. The interest in AI has grown with LLMs, but so have the expectations. The hype cycle that has promised a revolution that is unlikely to be realized in software, as it will not result in a silver bullet. Often the disillusionment that follows the failure of the hype of a technology is followed by a collapse in investment, but we also get a more realistic appraisal of the value of this good. It is at this point that we can genuinely understand how to incorporate these tools into our workflow. Of course, the evidence of previous waves of innovation and their attempts to find a silver bullet suggests that this point of realization might take some time to emerge. Yeah, and I think, so the conclusion is basically that you should try and learn prompt engineering. Start using AI assistants. Although this may be a problem for some enterprises, you have to be very careful what you can use. And the question is, though, whether these AI assistants will survive in case of an AI winter. That's still an open question. Nonetheless, they are interesting, they are useful, they can provide alternative ways of writing the code. They can come with ideas inspired by where their training base. It's not that they are generating those ideas, but they are part of their training set. And this is always useful. It's always interesting. So it might be that we'll need to develop new skills. And as I said, basically in the beginning, we still don't know. But it seems that what Jan is pointing at is that it's quite unlikely for AI to completely replace developers. And I tend to agree. Unless some fundamental development happens, is there another revolution coming after the LLMs into the world of AI? The rest of it will probably be incremental. And the question is whether the costs, whether there's really a business there, in fact. And we'll have to see about that. So, very interesting article. Very cool that Jan did this whole analysis. And I encourage you to go visit it and read it for yourself. I had skipped over a few parts, and I think it's worth studying, because it's something that is important for every software developer today. All right, this has been it for today. What do you think about this topic? Will AI replace programmers? Do you use any of these Copilot tools? Are they as useful they um, as they say they are? Do you believe there will be a revolution in AI? Let us know in the comments. We love comments, and we love being in conversation with you. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.